Hello, welcome. In this short video, let us look at an example in which we apply the properties of Laplace transform to derive the Laplace transform of a given signal. That is, we will use two properties. First one is translation in S-plane and second one is differentiation in S-plane. So we will apply these two properties to find the Laplace transform of a given signal. So the signal is x of t is equal to t square e power minus 2t u of t. That is, the unit step signal is multiplied by e power minus 2t and t square. So to find the Laplace transform, our goal is to find the Laplace transform of this signal. So to solve this problem, we need the following two properties of Laplace transform. The first one is translation in S-plane. So the first property is translation in S-plane. It is defined as the Laplace transform of e power at f of t, that is a function f of t multiplied by e power at. Then the Laplace transform of this product is given by f of s minus a. Here note that capital F of s is the Laplace transform of f of t. That is, f of t has a Laplace transform f of s. So in that case, e power at f of t, the product has a Laplace transform f of s minus a. So this is the translation in S-plane. Now we also have the second property, that is we need the second property, which is differentiation in S-plane. So this differentiation property is defined as the Laplace transform of the product, that is t square f of t is the second derivative of the Laplace transform of f of t, that is f double dash of s. Again, f of s is the Laplace transform of f of t. So we have to apply these two properties to find the Laplace transform of this product, that is t square e power minus 2t u of t. So the first step is step 1. We have to find the Laplace transform of the unit step signal, that is u of t, which can be easily defined as u of s is integral 0 to infinity u of t e power minus st dt. Since u of t is equal to 1 for all t greater than or equal to 0, for all t that is greater than or equal to 0, we have integral 0 to infinity e power minus st dt, which is clearly equal to e power minus st by minus s. The limits are 0 and infinity. So upon simplification, this will be simply equal to 1 by s. Therefore, the Laplace transform of the unit step signal is 1 by s. Now, step 2. We apply the property 1, that is, we apply the translation property, translation in S-plane. Laplace transform of e power at f of t is f of s minus a. So, let us call this Laplace transform x1 of s, which will be the Laplace transform of e power minus 2t u of t. That is the partial product in the given signal x of t. So e power minus 2t u of t, the Laplace transform is simply defined as u of s plus 2. That is, the Laplace transform of u of t, and s is replaced by s plus 2. That is s minus a, where a is minus 2. So it is u of s plus 2. And based on the result we have, it will be equal to 1 by s plus 2. Therefore, x1 of s, the Laplace transform of e power minus 2t u of t is 1 by s plus. And now finally, step 3, we have to find the Laplace transform of the given signal x of t. Therefore, x of s, the Laplace transform of x of t will be equal to the Laplace transform of x of t will be equal to, based on the second property, that is based on the differentiation property, t square f of t, that is Laplace transform of t square and then e power minus 2t u of t. So the Laplace transform of this signal will be equal to the second derivative of the Laplace transform of e power minus 2t u of t, which is basically x1 of s. So x of s will be simply x1 of s second derivative. That is the second derivative of x1 of s. And x1 of s is 1 by s plus 2. So this is going to be equal to d square by ds square 1 by s plus 2. So the first derivative is clearly now d square by ds square of 1 by s plus 2 can be written as is equal to d by ds of the first derivative of s plus 1 by s plus 2, which is minus 1 by s plus 2 whole square. And now the derivative of this function is minus of minus 2, that is minus 1 of minus 2 is 2, and 2 by s plus 2 whole cube. Therefore, the Laplace transform of the given signal x of t is 2 by s plus 2 whole cube. So to summarize, we have looked at the Laplace transform, or we have derived the Laplace transform of the signal x of t, which is equal to t square e power minus 2t u of t. So to solve this problem, we need two properties of Laplace transforms. The first one is translation in s-plane, which is basically defined as the Laplace transform of e power at f of t is equal to f of s minus a, where f of t and f of s are Laplace transform pair. Now, we also have the second property, that is we need the second property, that is differentiation in s-plane. This Laplace transform of t square f of t is f double derivative of s, that is double derivative of f of s. So we need these two properties. So step 1 for this finding the Laplace transform is we have to first find the Laplace transform of u of t, which is simply found to be 1 by s. Which is found to be simply 1 by s. Now for the second part, that is second step, we have to find the Laplace transform of e power minus 2t u of t. So by applying the translation in s-plane property, we have found that x1 of s is 1 by s plus 2. And then the final and third step, that is in the third and final step, the Laplace transform of the given signal is found to be based on the differentiation property, that is differentiation in s-plane. So by using this property, we found that x of s is second derivative of x1 of s, that is x1 of s is the result in step 2. So by simply applying the differentiation, we can see that x of s is equal to 2 by s plus 2 whole cube. In other words, the Laplace transform of the given signal t square e power minus 2t u of t is 2 by s plus 2 whole cube. Thanks for watching.